In this section, we're going to make more use of further derivatives. We've already looked at our first derivative and kind of dealt with that, but we're going to look at the second derivative and see how it can help us and what it's going to show us not only graphically with some of our functions, but also application-wise on how it can help us. So graphically, a function is either one of two directions. It's either concave up or concave down. If it's concave up, if its graph is curved with the opening upward, and so we can see this in figure A, we can see that this graph is concave up. Likewise, it's going to be concave down if it opens downward. And you can see this in figure B. Always kind of think about contacts. If you wear contacts, you're putting in an eye. It has a concavity to it. Or if you were to accidentally inside out it, if you're a contact wearer, you understand there. So if you accidentally inside out it, it kind of has a lip to it. So you can tell that the concavity of it is kind of off. And so I always kind of think about that direction when I get into these illustrations. When we get into graphs that are a little bit more curved to it, you can see something like this. Now let me kind of color code our notes as we work this. You can see that with this more curve of graph, this is concave up until it gets to this point. And then the graph is turning downward, and so it's concave down here in the middle. And then it turns again, and it's concave up. You can also note similarly that with this does not reflect the increasing or decreasing, because from this point to this point, the line is increasing. And from this point forward, it's increasing, whereas we're decreasing here and we're decreasing here. So we're beyond the point of increasing or decreasing. It's a more specific detail of the concavity of the function, and you can see those two ideas are different. Now we can't go any further with a problem unless we continue to look at the tangent. When you begin to look at these tangent lines at these points, you're going to see that this one is concave downward, and right here it has a tangent, and then when it's concave up, it's also a tangent. The derivative tells us the original function is increasing or decreasing, so this is your first derivative. And the second derivative tells us if the original function is concave up or down. And so you can see up here, my first derivative is telling me that red and blue, and then my second derivative is telling me the yellow and green. So furthermore, it says the second derivative, let y equal f of x. The second derivative is the derivative of our first derivative. Using prime notation, you're going to see a double prime mark here, or even y double prime, and you can read it aloud as I just said, y double prime. The second derivative can be written in other notations, such as these notations here. Again, read the second derivative of f. And here's where we get our concavity, or what we need to know. If f double prime of x is positive on an interval, the graph is known as concave up. And we can say that f is increasing or decreasing at an increasing rate. And if f double prime is negative on an interval, positive, negative, we can say it's concave up on that interval. We can say that we have a typo there, excuse me, concave down on that interval, and we say that it's increasing or decreasing at a decreasing rate. Now, it's hard to remember where f double prime is positive or where f double prime is negative, and to remember that it's up or down, and so I have some silly little symbols that'll help us with that. If you find that your second derivative is positive, it's going to be concave up, and this is your second derivative. If you find your second derivative to be negative, it's going to be concave down. And as lame as those smiley faces are, they are very helpful for remembering which direction that you are actually facing. And so let me show you some different things that we can do that. But I'm going to tell you, I'm going to refer to these smiley faces more than I will these words, because I think this is more memorable to figure out those details. And so let's go down to this example. It says find f double prime of x for f of x equals 3x to the 7th. Now I'm going to tell you this. When you're looking for the second derivative, there is no shortcut way. There is no way you're going to be able to just write the second derivative without finding the first derivative. So first step is you got to take the derivative. So it gives me 21x to the 6th. Then in order to find the second derivative, that would be equal to, just apply your power rule again. So bring that 6 down. 6 times that 21 gives you, 126, x to the 5th. And so if I were given points out for this and say this was worth 6 points, I'd give you 3 points for the first derivative, 3 points for the second derivative. Now remember, when you're working through these functions, the first one tells you your position in an application problem. The second one tells you velocity in the problem. And the last one tells you the acceleration in the problem. We saw this at the end of 2.5 as well. We were dealing with that arrow that was moving up and down. And so as we move into this next example here, it says the height feet of a particle at time t seconds is equal to f of t. Find the height, velocity, and acceleration of the particle when t is equal to 0, 1, and 2. And so what's interesting with this one is that as you're working on this, so your height is going to be your original function. So if I'm looking for the height function, this is that f of t equal to t cubed minus 4t squared plus 8t. So if I want to find the height at 0, I'm going to just say f of 0. So it would be 0 cubed minus 40 squared plus 8 times 0. So the height's just 0 because it hasn't moved anywhere. Then if I'm going to go after 1 second, again, I'm just going to plug in 1. Use my calculator here. And so let's see, that gives me a height of 5. And then I'm going to say after 2 seconds. So 2 cubed minus 4 times 2 cubed plus 8 times 2. I'm just going to plug all that directly in. And that gives me a value of 8. And so this is feet. And this is our height after 0, 1, and 2 seconds. But if I take it further, I'm going to switch colors here. Let's now look at velocity. Velocity is the derivative of that. So my velocity function is going to be my derivative of my height function. So I'm going to take the derivative of this one here. So it would be 3t squared minus 8t plus 8. And then you rinse and repeat and plug in your information there. So f prime of 0 would be 3 times 0 squared minus 8 times 0 plus 8. So it just gives me 8 feet per second. So after 0 seconds, my velocity, or really my initial velocity, is 8 feet per second. F prime of 1, again, just plug in 1, is going to be equal to, grab your handy dandy calculator, and you get 3 feet per second. And then your velocity after 2 seconds is just plugging in 2. So calculate that out. It gives me 4 feet per second after 2 seconds. So now that I have the height, the velocity, I need to move into acceleration. So acceleration, a of t, is equal to the velocity function derivative, or the second derivative of your height function. So I'm going to take the derivative of where I left off here. That would be 6t minus 8. And then again, I'm just going to plug in what is the acceleration after 0 seconds. That's negative 8 feet per second squared. What is the acceleration after 1 second? Just plugging it in. It gives me negative 2 feet per second squared. And what is the acceleration after 2 seconds? Let's see, that would give me 4 feet per second squared. And so to kind of give you a better idea of what's going on with velocity and acceleration, let me make some notes up here. When you're driving your car, the speedometer is your velocity. Okay, the speedometer is your velocity. The gas pedal and how hard that you're pushing on the gas pedal or not is your accelerator. And so hopefully that kind of helps make more sense of what's going on with velocity, acceleration, and the difference between the two. But in the case of this problem, you can see they were just asking you to take the derivative and then take the derivative again. They didn't flat out say that, but you have to know that by these keywords of velocity and acceleration of that particle. Now, as we move into the second derivative, we've got to pick up a new vocabulary word, and that vocabulary word is an inflection point. An inflection point is a point on the graph of a function where the concavity of the function changes. So that's going to be where it changes from concave up to down, or from concave down to up. And so if you'll notice here in this example, it says, which of the labeled points in the graph below are inflection points? So you're looking for where the concavity is changing. So let's just kind of look at this. Where's this one concave up? You can see it's concave up from here to here, and then it begins to come down. It's still concave downward, it's still concave downward, and then from here to here, we have it concave up again. And so we can see it's up where we've highlighted in green. It's concave down from here to here, and notice it's still concave down. It's still concave down, even though it created a cusp here at E. And so if we go back to the problem, it says, which of the labeled points in the graph are inflection points? Well, B would be an inflection point, and G would be an inflection point, because it's only where the concavity is changing, not necessarily where you have a new curve. So be careful with that. A more working definition would be an inflection point is a point on the graph where the second derivative sign changes, because we're not always given all those different curves. We just look at it and pick out two letters. And so in order to find the inflection points or where the second derivative signs changes, here's what we're going to do. And let me write this down for you. To find inflection points, you want to look at f double prime of x, where it's either equal to 0 or undefined. And then what you're going to do is you're going to check the signs from there. And so let's kind of look at this next example, and I'm going to walk you through it. And then once we kind of walk through this simple example, I'm going to show you what's going on. And so let's look at this example. It says, let f of x equal g of x equal h of x equal. We got three different graphs. For which of these functions is the point 0, 0 an inflection point? And so I want to start out pretty basic. Okay, where is its inflection point? So we want to know, where is the concavity changing? And so just similar to the one we did here, I'm going to use my highlighter. You can see that it's concave up from here to here. This one's concave up the entire way, and this one's concave up from here to here. Where is it concave down? That would be on this side. There's no concavity where it's downward, and then concave down here. So going back to the question, for which of these functions is the point an inflection point? 0, 0 is an inflection point on this first one and on the second one, but it is not on the middle one because the concavity was not changing. So graphically, yeah, that's the way it looks. But let me show you the algebra behind this while we have these graphs up here invisible. So if you look at your f of x function, that's equal to x cubed. Concavity is based on your second derivative. So I'm going to take the first derivative, and that's equal to 3x squared. And I'm going to take the second derivative, and that's equal to 6x. Now I just told you to find the inflection points, that's where the second derivative is equal to 0 or undefined. So I'm going to set this equal to 0 and solve, and I get x to be 0. And so if you take a number line and look at that inflection point you just found, which was at 0, and then if you plug in values to the left and right of 0 into your second derivative, you'll figure out what the concavity is going to look like. So if I were to plug in -1, f double prime of -1 would be equal to 6 times -1, which is -6. And all I care about is that it was negative over here in this test area. And so if I segregate out my areas from my inflection point, I can see it's negative over here. If I plug in f double prime of, say, +1, I would get 6 times 1, which is 6, which is a positive number. So I could see it would be positive over here in terms of my second derivative. This tells me that, using my handy dandy smiley faces, it would be concave down over here. It would be concave up over here. And right there at 0, I had an inflection point because the sign changed. So pretty interesting that we can look at the algebra of it without the graph and figure that out. Let's do it again with the second one where we didn't have one. So g of x is equal to x to the fourth. So that means g prime of x was equal to 4x cubed. And g double prime of x will be equal to 12x squared. So I'm going to do the same thing. I'm going to set it equal to 0 and solve, which again gives me 0. So I'm going to draw a number line at 0. And I'm going to check to the left and right of 0 into my second derivative. So if I plug in, say, -1, plug it into my second derivative, that would give me 12 times -1 squared. Well, -1 squared would be 1 times 12, so it would be positive. And if I plug in, say, +1, that squared is really just going to take away any sign change that I have. So again, it's going to be positive over here. So this is why you can see that we have concavity on g of x, even though I was able to solve for this point, by checking it with this number line system, I can see what's going on with it. And then we can follow the same process for the last one, h of x. And so I think it's important to show you how algebraically it's working out, because the luxury of these graphs, because we're not using a graphing calculator, is not always going to be there for us. Now, before we move into any more examples or exercises, I want to take a minute and define some things and show you two important tests that really kind of help us out. The first thing I want to define for you is the idea critical numbers. And what are critical numbers? Critical numbers are where something is happening, and it goes all the way back to your first derivative, and it's going to be where minimum values are occurring or maximum values are occurring. And so we say that critical numbers or where f prime of x is going to occur is when it's equal to 0 or it's undefined. Because remember, f prime of x equal to 0 is where your horizontal tangents are going to lie. And so how do I find critical numbers, and how do I figure out that they are minimums or maximum values where that horizontal line to the tangent is? We have something called the first derivative test. What the first derivative test does is it helps us to take those algebraic functions like we were seeing in the previous example, break them down, and find all the different points that we need in order to graph or to find values, to find maybe possibly the maximum profit, the minimum cost, or things like that. And so here we're going to use something called the first derivative test. This is used to find the intervals of a function where it's increasing and decreasing, and then based off those intervals, we can make more statements of maximums and minimums. So we're really finding all those curves of these graphs that we've already been looking at. So it says if f prime of x changes from a negative to a positive, so if we change from a negative, which is decreasing, to a positive, which is increasing, then we have a minimum. And that is true because you can see it's going downward and then upward. And so in regards to our graph, it would mean that we had a minimum value here. If f prime of x changes from positive to negative, so we're going from a positive or a slope that's going upward to a negative or slope that's going downward, then we're going to have a maximum. And again, this would be such as on a parabola, this point here give us a maximum value. And then if f prime of x doesn't change, then it's either neither a max or min. And so we're going to take what we know about increasing and decreasing functions and apply it and go, you know what, now that we know it's going down and then upward, here's where we're going to have a minimum value, or here's where we're going to have a maximum value. Or if neither of that's happening, it's not changing over, then it's not a min or max. So how do you even apply that? To apply the first derivative test, you have to find the critical values. And so you have to find where f prime of x is either equal to 0 or does not exist, undefined, etc. Then you're going to test your intervals around those critical values. It's going to be similar to what we saw in that last example, where you're going to draw a number line, look at values based off f prime of x, and figure out what's going on. And then you can state your increasing, decreasing, or any maximum or minimum values. And so the first derivative test is really nice. It helps you find the increasing, the decreasing, and then looking at those patterns state where you have maximum values. And again, this would come in cue with your maximum profits or minimizing your cost. So that's looking at your first derivative test. But if you're looking at the second derivative, which we've been doing a lot in this lecture, that brought in inflection points. And so we learned that points of inflection were changes in concavity. Now that's going to occur when your f prime of x is equal to 0 or your f double prime of x does not exist. And so it's interesting to note that in your first derivative test, you're working with the first derivative equal to 0, it does not exist, and critical numbers. Your second derivative test, we're going to be looking at points of inflection. But the second derivative test is really nice because in the first derivative test, we had to test all these different values. We had to draw a number line. Well, if you can take what you know of critical values, plug them into your second derivative, then just based on your concavity, you can find where things are minimum and maximum. And so that's why I kind of want to pull in all of this information here, is because we were just looking at concavity. And so I wanted to show you this second derivative test. And so how do you do that? You find your critical values, test your critical values in your second derivative, and based on if it is positive, you're going to have a minimum, and that'll go back to our smiley faces. Or if it's negative, you're going to have a maximum. And so I'm going to do an example of that second derivative test. Is find the minimum and maximum values for this. So the first thing you're going to do is find your critical values, and that involves your first derivative. And so I'm going to find f prime of x is equal to, I'm going to take the derivative, negative 15x to the fourth plus 15x squared, and I'm going to set it equal to 0 and solve. So you've got to be a master of solving here. I am going to factor out a GCF of negative 15x squared. That leaves me with a that leaves me with an x squared, neaten that up a little bit for us, minus 1 equal to 0. And then I can solve this out, so I could say negative 15x squared equal to 0, and that would just give me 0. I could say x squared minus 1 equal to 0, so that'd be x squared equal to 1. So x would equal plus or minus 1. And so those right there would give me critical values of x equal to 0, negative 1, and 1. Now what your second derivative test says, now test those in your second derivative. So we're going to have to come over here and say what is f double prime of x. So I'm looking at my first derivative, and I'm going to take the derivative of that. So that would give me negative 60x cubed plus 30x. And we're going to, so now we have our second derivative that we can plug in, and we're going to take these three values we already knew to be critical. Something is going on there, and instead of testing left and right, doing number line like we saw in that previous example, we're just going to plug them into our second derivative, and then based off the signs that we get, we can state if they're minimums or maximums. And so I'm going to say f double prime of 0, that would be equal to negative 60 0 cubed plus 30 times 0, and that's just going to give me 0. So that's not very conclusive. We'll have to result back to the first derivative test. If I go to f double prime of 1, that gives me negative 60 times 1 cubed plus 30 times 1. So that gives me negative 60 plus 30, which is negative 30. And so because it's negative, I'm going to think about my smiley face there, I know that I'm going to have a maximum value at x equal to 1. Let's look at our other value, f double prime of negative 1. That would be equal to negative 6 of negative 1 cubed plus 30 times negative 1. So let's see, that would be negative 1 cubed stays negative, so negative and negative gives me a positive 60 minus 30, which gives me a positive 30. So at the critical value of negative 1, I could see, smiley face, that I'm going to have a minimum at x equal to negative 1. And so you can see this second derivative test, and knowing what the concavity is and using our Super lame smiley faces. We have been now able to jump course and find what the minimum and maximums are. And so just to finish out this problem, we're going to have to go out and find what's going on at 0. So you're going to see some examples of our first derivative test. Now let's go ahead and grab that first derivative again. So we said the first derivative was equal to negative 15x to the 4th plus 15x squared. And so I'm going to take this and I'm going to draw a number line. Now I'm going to put all critical values on here. And so we have a value at negative 1, 0, and 1. And what you do is for that first derivative test, which we're going to have to result back to for the 0 value, is you take and plug in values into f prime of x. And so we're not going to plug in values at critical values. We are just going to see what's going on with them. And so we're going to say, what is, say, f prime of 1/2? And that'll give us a value right in here. That would be equal to negative 15 of 1/2 to the 4th plus 15 of 1/2 squared. So using our calculator, we get f prime of 1/2 equal to the value 2.8125. And really, I'm just only concerned that that's a positive number here. So we've got positives going on here. Now, based off what we just saw on the other side of positive 1, we know that that was a maximum. And so we know we're going to get a negative over here. And you could pick a value, say like f prime of 2. You plug it in and you get a negative value. And it doesn't matter what that number was. We just know it's going to be negative. Now, if I take and I plug in f prime of negative 1/2, this will give me a value here. So again, I'm just going to plug in negative 1/2 to the 4th plus 15 times negative 1/2 squared. I'm going to go on my calculator and I'm just going to go into what I just typed in and change those 0.5s into negatives. And that gives me f prime of negative 1/2 to be 2.8125. Again, it's positive. And so we can see why that second derivative test wasn't working out for us, because we already know negative 1 is a minimum. And so from the first derivative test, what happens is you can go, oh, that's decreasing, that's increasing, so I have a minimum here. Okay, that's increasing and then decreasing, so I have a maximum here. But you can see what's going on here. It's a positive and then a positive. So although 0 was a critical value, we already saw from the second derivative test, it was not distinguishable if it was a minimum or maximum. And we see here in the example of the first derivative test, again, it's not distinguishable. That's a minimum or maximum. It's increasing and then increasing. Probably at this value of 0, it's just a matter of it was changing slopes of how it was increasing, maybe something like this of sorts. And so you can see it's still increasing, but it kind of slows down there in the middle. And so I want to kind of just show you a little bit of this first derivative test, but mainly I want to show you how the second derivative test is really helpful based off the concavity. Again, the concavity, we were able to figure out maximums and minimums. Now let's look at some examples of everything we've talked about in 2.6. It says, on which intervals is the function of the graph concave up or concave down? And so I'm going to use my highlighter here so we can see where it's concave up is from here to here. Where is it concave down? We can see it's concave down here. And so it says on which intervals. I'm going to use interval notation. It's concave up from 3 to 7, and it's concave down from 0 to 3. So be able to read your concavity from a graph. Let's do another one. On which interval is the graph concave up and concave down? So concave up, we can see, is going to be in this grouping. It pauses and it concaves up again. And then we're concave down, then we concave up here. And so you're looking for where that concavity is changing. Here's that concave down. Be careful with little areas like this. So my intervals of where it's concave up would be between 0 and 4, unioned with from 6 to 9, and then it would be concave down in the middle there from 4 to 6. Let's do another example of what we've been seeing in this section. In this one it says, in the problems below, a function and values of x so that f prime of x equals 0 are given. Use the second derivative test to determine whether each point is a maximum or minimum. And so first thing we're going to have to do, if we are using the second derivative test, we got to find the second derivative. And so I'm going to first find the first derivative, f prime of x. That would be equal to 6x squared minus 30x. I'm going to keep rolling and find my second derivative, and that would be 12x minus 30. Now they've already told me that these are the values that I'm wanting to check what's going on. So I didn't have to go through all the steps of critical values like I was showing you in the examples. And so I'm going to say, what is f prime of 0? Well, that would be 12 times 0 minus 30. That gives me a negative 30. Because it is negative, my smiley faces, I know that I'm going to have a maximum at 0. Let's do it again with our other values. So f double prime of 5 be equal to 12 times 5 minus 30. And so let's see, that would be 60 minus 30 to give me a positive 30. And again, I'm not concerned that it's 30. I'm concerned that it's positive. And so again, super lame smiley faces. Then this shows me I'm going to have a minimum at x equal to 5. So you can see that rolls pretty quickly, especially when they give you these values. Now let's do it again. This derivative is going to be a little bit difficult for us. This is a product function. I'm going to have to remember some rules here. So I'm going to say f prime of x is equal to, let's do the product rule, derivative of the first times the second plus the first. The derivative of the second is 1 over x. So I'm going to clean all that up. That's ln x plus 1. Then I'm looking for my second derivative, so I'm going to do the second derivative. That would be equal to the derivative of ln x, which is 1 over x, plus the derivative 1, which is just 0. And so our second derivative cleaned up really nicely. So I'm going to say, let's look at the value of 1 over e. So I'm going to say second derivative, plugging in 1 over e would be 1 over 1 over e. I'm going to write this horizontally so that I can keep it, change it to multiplication, and flip the second. And this just gives me a value of e, which is a number. It is a positive number. And so the fact that it is a positive number, I can use my super lame smiley faces. And so I'm going to say that I have a minimum at x equal to 1 over e. So you can see that second derivative test flows really nicely for us. Next part, it says, which of the labeled points in the graph are inflection points? Remember, your inflection points are where your concavity is changing. And so I'm going to say, okay, just look at our concavity here. This is concave up. This is concaved up. Concaved up. This is concave down and concave down. So where are my concavities changing? That would be at B, D, and H. Don't let that fool you. And so what are the labeled points? It would be B, D, and H. Next one has us looking at quite a bit. It says fill in the table with positives and negatives or 0 for the function showed. So first thing I want to do is let's look at 0 and let's fill in our f of x. So at 0, it's going to be at a positive value. At 1, it's a positive value. And these are just all the y values. Since they're all above the x-axis, these are actually all positive. Then we're going to look at the derivative. Now don't forget, the derivative is slope. And so if I look at 0, you can see that it's going upward or increasing. And so that would be positive. At 1, you can see the tangent would be going downward, so that would be negative slope. At 2, you can see it's zeroed out, so that would be 0 slope. And at 3, we can see it's going up again, so it would be positive slope. And then the last one, you're looking at the second derivative. Now remember, with your second derivative, that is concavity. And with concavity, if it's concave up, it's going to be positive. And if it's concave down, it's going to be negative. And so let's see. it's concave down when we get to this point, and then it looks like it's concave up for the rest of the way. And so when we go to fill in our positives and negatives, at 0, it was concave down, so that's negative. At 1, it's kind of the changing of the concavity, so we're going to say 0. At 2, it's concave upwards, that would be positive. And at 3, it looks like, now I'm looking back at it, it looks like it's starting to change over to concave down. Like it looks like it's starting to make a change. And so we're going to say that that has a concavity of 0. And so really interesting, just putting all of our concepts together, we can see where is the concavity, where are our slopes, where are things changing. Now let's jump into some problems here and just keep practicing through our derivatives. And what I want to do here is I want to find the derivative and the second derivative of each function. So I'm going to start with the first derivative. The first derivative is equal to, I'm going to do my power rules, that would give me 14x plus 5. Hopefully this is review. You're understanding this. You're picking up those rules. Maybe pause it, see if you get the derivative and match it up. Then my second derivative would be just 14. Next one amps it up a little bit. We got to use our chain rule. So the first derivative would be bring down the 10, leave the inside alone, subtract 1 from the exponent, times the derivative of the inside, that would be 6 minus 2x. Now the really only cleanup we could do is we could distribute the 10 into here. We can't put it into here because the 9 is guarding it. And so I'm going to say that is 60 minus 20x times 6x minus x squared to the 9th. And I cleaned it up like that so that when I now go into my second derivative, I'm not dealing with too many pieces. Now for the second derivative, we do have two functions here. I have one function here and one function here. So I'm going to have to do product rule and chain rule with this one. So the derivative of the first would be negative 20 times the second, 6x minus x squared to the 9th, plus the first, 60 minus 20x times the derivative of the second, which the derivative of the second would be 9 times 6x minus x squared to the 8th times the inside, which is 6 minus 2x. Whew, that's pretty long. So you can see your cleanup's going to help you to get those derivatives a little bit better. We could put some of that together, but for now I'm just going to leave it as is. Let's look at this radical. So I'm going to first find the first derivative. Now, before I start in on that, I do want to rewrite this and do some algebra. X squared plus 6x minus 1, that's being raised to the 1/2 power. So when I come down here and do my first derivative, this would be 1/2 x squared plus 6x minus 1 to the negative 1/2 times the derivative of the inside, which is 2x plus 6. Similar to what I did in the last problem, I'm going to take that 1/2 and distribute it in here. So that gives me x plus 3 times x squared plus 6x minus 1 to the negative 1/2. Now if I was stopping with this, I would take this further and say let's do that x plus 3 on top, and let's put the square root on bottom. X squared plus 6x minus 1. That would be a really nice first derivative. Now you can take that really nice first derivative and do second derivative, or you can keep working right here with your product rule if you like, and that's what I'm going to do for my second derivative. So I'm going to say the second derivative is equal to, and again I'm working on this function here, although this is the nice cleanup. Now this one's going to do product rule, or this one would do quotient rule, but they would all pan out to be the same thing. So I'm going to work with here and do product rule again. So I'm going to do derivative of the first times the second plus the first times the derivative of the second, which would be negative 1/2 x squared plus 6x minus 1 to the negative 3/2. Be careful with those fractions, times the derivative of the inside, which is 2x plus 6. Now I am going to clean this up a little bit. I know that sounds enjoyable for you. This right here, this grouping, you can see I have in both terms. And so when you're factoring out what they both have, you take the smallest of the two exponents, and this is actually the smallest of the two exponents. So I'm going to pull that out front. This would give me x squared plus 6x minus 1 to the negative 1/2. Now in the first term, I'm taking out the negative 3/2. So in the first term, when I take negative 1/2 minus negative 3/2, actually just leaves me with x squared plus 6x minus 1. In the second half, I'm taking out that whole piece there. It's all coming out front. So I am going to distribute this negative 1/2 into here like I did before. So it gives me plus x plus 3, and then negative 1/2 of this would be negative x minus 3. Whew, almost done. So that gives me x squared plus 6x minus 1 to the negative 3/2. I'm going to clean up this. This is x squared plus 6x minus 1. I'm going to FOIL this thing out, so that gives me minus x squared minus 3x minus 3x minus 9. And I did all that so I can clean this up. I know that sounds odd, but x squared and negative x squared would cancel. 6x and these negative 3x's would cancel. Negative 1 and negative 9 would give me negative 10. So this is actually negative 10 over, and I'm going to put this on bottom. X squared plus 6x minus 1 to the 3/2. Algebra, algebra, algebra is what's going to get you. So this here is my first derivative. This is my second derivative. But you can see why I would clean all this up, because this is much more user-friendly than this long string that I had in my raw derivative. Now that I've scared you with that one, let's do two more examples. And so let's do this one. What would be the first derivative? That would be 6 times 2x cubed plus 3 to the 5th times the derivative of the inside, which would be 6x squared. Cleaning that up, I think that phrase scares you now. That gives me 36x squared times 2x cubed plus 3 to the 5th. Now let's do f double prime. So that's going to be product rule. So I'm going to do derivative of the first, which is 72x times the second, 2x cubed plus 3 to the 5th, plus the first, 36x squared, times the derivative of the second, which would be times 5, 2x cubed plus 3 to the 4th, times the derivative of the inside, which is 6x squared. Now, you probably are just dying to clean that up, but I'll save that for you, and you can clean that up on your own. And then this last one, we would say f prime of x is equal to 2x minus 8. You would bring the 5 out front, subtract 1 from it, times the derivative of the inside, leaving me with 10 times 2x minus 8 to the 4th. And then our second derivative would be, bring down that 4, so 40, 2x minus 8 to the 3rd, times the derivative of the inside, which is 2. And so cleaning up, we get 80 times 2x minus 8 to the 3rd. And so I wanted to do a lot of examples here at the end of first and second derivatives and different values of functions so you could help with that. Now, I know this lecture went really long, but I'm hoping these examples will help you to better work through the problems. Let me know if you have any questions along the way.